chair had, Margaret, was he was worried that he couldn't speak English. Well, I think you can see his English is pretty good. That wasn't hard to find out. I just called him up. So anyway, we're here. I'm also proud to say he's a member of my laboratory, which, maybe, we're known to say controversial things. I don't know if I would have said that one, but, if anything, I see machine learning is on the rise, and, it'll be hard to dislodge signal processing from many, many fields. But anyway, with that being said, we might as well let you state your piece. Alex has been working developing an end-to-end pipeline to process imagery from a 3D microscope in my lab that are labeled up with various things to link, cellular function, with informatics elements. So, maybe you'll hear something about that. He uses the Loney pipeline for part of that, which is, was developed by Art and, Evo over many, many years. And, it's standard image processing pipeline for radiological images, brain imagery, and all this kind of stuff. It's world standard stuff. There is one of the BD2K centers, which is now at the University of Southern California, which I believe has two, one of which Bing is involved in. Is housed there. Art moved from UCLA to the University of Southern California about a couple of years ago now. So, Alex, why don't you go ahead and give us a start? And his interest really is data science. So, let's see what you've got on your mind. We're looking forward to hearing about it.
Okay. Hi, everybody. So I'm Alex, and I am interested in data science, but particularly in machine learning and applying it to biomedical images. That's what we are doing with Dr. Reda in his lab. And this particular talk is about deep learning, which we are not currently using in our lab, but we might be in future after I successfully present on it. And so, yeah, the title, I know, right? I want to say that's just because I want to emphasize the knowledge that it's a buzzword. It was around for a while, for a couple of years. It was on the front page of the science section of the New York Times and other different papers. But as an answer, as referring to that question, I can give you a short answer right now. No, it's not. It's not the end of machine learning signal processing. But thank you for coming. I'm glad to see so many people maybe reacted to this provocative title. But I do think that the collection of those methods, they are important, and they do give good results, and they do deserve some attention paid to that. And I would like that biomedical and bioinformatics researchers, that society, learn more about these methods. So that's the motivation for this talk. And as a just brief introduction for those of you who are not very familiar with neural networks and deep learning in general, so deep learning is based on neural networks, which are biologically inspired models for learning from the data. And the deep learning, it's actually a wide set of different algorithms that are mostly based on neural networks that allows efficient learning on the data. And that's the classical, typical structure of neural network. They were developed in the middle of 20th century. That's the model when you have entities that are called neurons in analogy with the brain. And it's basically what it does. It approximates some unknown function based on the input nodes towards the output node. And how it works, it basically the model that have weights that are calculated in a way taking these values from input nodes, calculating using some embedded function that's called an activation function in a middle layer, which are also often called hidden layer. And then there is an output node that represents itself as an output of unknown function. And what's the difference between usual networks and deep learning networks? That they have multiple layers of nonlinear processing units that are in middle layers and hidden layers, and they can do unsupervised learning but more importantly, they do it with a they do learn feature representations on those layers. And when you have many middle layers here in the middle, those feature representations, they start to form a hierarchy from low level to high level features. And yeah, a little bit of historical perspective. So an answer invented in 1950s. At the same time, people already tried to do multi-layer neural networks. Multi-layer perceptron was invented in 1957, but later those techniques they were not showing great performance, and they were outperformed by new algorithms such as support vector machine or later random forest. And the reasons why they didn't work well at that time, so the process of training and the backpropagation was too slow, and it was not enough data. And I should mention the backpropagation process is the specific for neural networks. So at the process of training, from the input data, the weights of the model are getting defined, but later when you get the output of the unknown function, there is an algorithm that's called backpropagation that allows to update the weights in the middle layer, so the learning process can be reiterated again with the new weights, and it's conversion to the optimal weight set.
So I think another problem, and I'd like your comment on this. I mean, my perception, at least, of the neural nets was that they were kind of a black box at the end of the day.
I will talk a little bit about it. Yeah.
Huh?
I will talk.
Yeah, I think this is really an important thing, because this is the computer scientists had a very negative, kind of attitude about the neural nets because of that.
So yeah, one of the objectives.
It's kind of old information, but I think it's probably still true.
Exactly. So one of the objectives of this talk is to give an update on that opinion.
Good.
So how did we get here? That's basically everywhere. It's in New York Times. That's in papers, in science, and Google is working on that. And recently, Microsoft said that they can recognize images better than humans do.
Oh yeah.
So basically, since that time, since the neural networks had their first renaissance, some things changed. First of all, new algorithms were introduced. One of them is very important, is layer-wise training algorithm by Geoffrey Hinton from the University of Toronto, who published a couple of papers in that year, including one in Science. Now we got larger data, much larger than now, and Dr. Avi is going to give a talk soon, I hope, about the big data hype in a couple of weeks.
Don't shoot me.
He's going to talk about number 2 in this list, so I'm going to sort of leave it for him now. And now we got much more computing power, which is obviously because of the Moore's law and the GPU computing and some new algorithms, because the rise of deep learning also gave boost to the not only to the hardware and data, but a lot of progress was done in algorithm development. And first, I'm going to talk about some results that were demonstrated with using deep learning, and then I will go a little bit into how they work. So just some examples where deep learning algorithms were performing much better than any other models and beating the benchmarks by other models. For example, the traffic sign contest, pedestrian detection that is used by different companies and universities, for example, for self-driving cars. And as you might know, there is one polygon that is under construction near Ann Arbor, where they're going to test self-driving cars. So these algorithms are working and getting be used in those applications. One important application in computer vision is image classification. So there is a very famous, in the field of computers, there is a very famous data set called ImageNet, and there is a competition every year where different teams from industry and academia, they compete to show the lowest error rate. And error rate for some time was around 25%, and at 2012, in this work by students of Geoffrey Hilden, the error rate on this data set was dropped by 10% to the 15%. And those improvements that they made for deep learning algorithm, they were called breakthrough in computer vision.
So
Also,
now it's only 4 or 5%.
I'm sorry?
The error is now 4 or 5%.
I will mention later. Yeah. So they also used in the scene parsing when they're trying to classify the different areas of the image, if it's a grass or if it's a sky or if it's people in the image, or scene parsing from that image, including using the deep learning on Microsoft Kinect.
So is the big breakthrough the multi-scale? I mean, what's the big breakthrough here? You know, we've been trying to do this for a long time. So what is the fundamental breakthrough that, you know, goes back to 2006? I mean, I don't know the answer to this, although I could guess. I think you know exactly the answer.
So
using architecture, right?
how models were built and algorithm that they used. Before that, the algorithms could classify only 75% of those images, and when after this work was done, they bumped up 10%.
Well, no, I know that part.
Yeah.
It's even better. But what was the underlying technological breakthrough that allowed that improvement to it?
Oh, that's how they constructed the network and the algorithms that they used.
Architecture of the network.
How many middle layers were put in a network? How they were interconnected in between themselves. That was the.
And were those?
I will. So
okay,
these are the results, and I will mention them later. So yes, screen parsing, scene parsing, some results on that, and the recent result on the ImageNet.
Fast. I mean, what's parsed in those screens? What did they do?
In the scene, I already mentioned that they're trying to parse the different items on the image. So trying to classify where is grass, where are trees, mountains versus skies. That was a pretty, heavy-duty task in computer vision for a long time. And only recently, only in past, I would say 10 years, after 2012, they start to actually be able to classify that with a high accuracy. So that was important achievement. And as it goes to ImageNet classification, just recently, literally this month, in a paper published by Microsoft researchers, they surpassed human-level performance on ImageNet classification. So humans could, error rate on that data set of image classification was around 5%. And in that work, researchers reported below 5% test error on the ImageNet image classification.
Just for curiosity, what is the main reason of human errors here? Because I can't imagine a human look at a photo and say that this is not the sky, this is the ocean on the above, or something like that.
No, humans do make errors. So there is a whole bunch of images, and sometimes when you go through them, with the hundreds of them, they're not all clear like this, right? And for example, this might be classified, I don't know, as a bug or something, right? So humans do make errors, especially on a big amounts of data. So that was another study that I did not include in slides, where the guy from Stanford University, from computer science, he was trying to beat a deep learning model by Google. So Google achieved something like 7% accuracy on ImageNet data set classification, and that the guy just sat through the ImageNet and tried to classify images in a row as accurate as Google, and he beat that. But for that, he needed to classify like 10,000 images. So and right now, this model performs even better than known human level accuracy on the image set. So now we go to something more interesting and related to studies at this department. Deep learning networks, they become a standard method in connectomics and studying volumetric images from the brain, and basically how they work in images like that. They go we are sections of the 3D image 7 by 7 by 7 neighborhood and classify if it's membrane or non-membrane. That's the task in connectomics. That's another work that have been done in that area, and there is a visualization of the multi-label classification performed by deep learning method. Also, it was used for biomedical image segmentation. So basically, this was pixel labeling with big convolutional neural networks that I will mention later. And what it does, it takes the window of pixels and produces a label for those pixels, for the central pixel related to the neighbor pixels. And also, they used the probabilistic graphical models to clean up the images to achieve the clear classification that is shown on the bottom row. Another application that I can give an example on is breast cancer cell mitosis detection. So basically, they were getting the histology images to 2D images, and from those images, they were classifying candidates for cell mitosis and using the deep learning network. And they since 2011 they achieved the highest accuracy in the field, and it's also become pretty remarkable result and the standard method for that. But it's not only used for image processing, but also, for example, for studying splicing isoforms. There is a publication in Science just in the beginning of this year where the team of researchers used deep learning algorithms to reveal the new insights of splicing relations to different diseases. They used it to classify, correlate DNA elements with splicing levels in different human tissues. So as you could see, the deep learning relies heavily on features, and for that, feature extraction itself is pretty important process. And one of the good properties of the deep learning, that I already mentioned in the beginning, that it builds the hierarchical representations of features. So basically, how it works, just to give you some understanding, is it takes an image as an input, for example, as it's basically 2D data with some intensities in different channels, and then on a first layer of the frame of the deep learning framework, there is some very simple features like edges or abstract, representations, and then as it goes through levels and it learns more and more something hierarchically constructed from the more simple features. So basically, at the higher levels, you have something more related to the picture than on the first level. So that's another example from the face recognition project, which is actually done by Hongdang Lee, who is now with CS department here at the University of Michigan. And that was another pretty famous paper on the face recognition. They described how this feature hierarchy builds up in levels of the convolutional neural network. So basically, in a nutshell, it works like this. For image recognition, the feature hierarchy builds up as from pixel to edge to text on motif part object. For text, it goes from characters, word group, close sentence, story, and for speech, through the other entities that are specific for the speech processing. So basically, the representations of this data is performed by discovering and distilling those independent explanatory factors. Another property of the deep learning network is that there is an assumption about the natural data. It's called manifold hypothesis, and the assumption is the natural data lives in low-dimensional nonlinear manifolds. And then task of the classification algorithm would be just to separate a bunch of tangled manifolds. For example.
So what's manifold? I know there's a lot of people that are kind of, what do you mean by manifold?
So manifold is a it's like a topological entity, I would say, that preserves Euclidean properties in each local space. But I'm not sure that helps a lot. So I would say that's in 2D that's a plane, and 3D that's like a surface that you can think about it like this. That's like a something that can be represented in a few dimensions. And if you take a look at this example, for example, if you think about image of the person or about face of the person as a manifold, and then you want to try to estimate how many dimensions does it have, you can think about it that the face has 3 Cartesian coordinates and 3 Euler angles. Euler angles when it rotates to different angles, and they have about 50 muscles in the face. So basically, the manifold that can describe the face of the person would have these 6 dimensions and 1 dimension for each muscles. We better can be you know, deforming sort of the face that can be considered as a different dimension. So that's the maybe intuitive idea of the manifold. So basically, one example of the difficult classification task, non-linear classification task, would look like this: when you have a data that classes of which cannot be separated linearly. And for that, some works on neural networks show that the neural networks starting from 2 and higher layers can actually deform the space in such a way that it becomes those classes become linearly separable. So that's the insight on how deep learning works from the topology viewpoint. And if you consider something even more complicated, such as when you have one class completely surrounded by another class, which would basically be a pretty big problem for a lot of classification algorithms, deep learning with enough hidden layers can disentangle those manifolds in a increased space, basically. There are some situations when even when depth of the deep learning method cannot completely resolve the problem. For example, when you have 2 classes that are sort of like 2 thoruses tangled to each other, and then the representation in a higher dimensional space would look something like that, but it's still not linearly separable. And those connections like this, they called links in topology. But still, even when the data topology of the data have those links in itself, deep and wide enough deep learning models still can show the pretty good classification result, untangling them in such a way. There still be error rate because of the link here, because of the connectedness here, but the results the ability of deep learning to do the disentangling of the manifolds, that shows better results than most of the other models. And now I just want to go briefly through a couple of very important deep learning architectures. So basically, how those models are built. One of them is, I guess, the most famous convolutional neural networks, and most of those results that are achieved maximum accuracy on a lot of computer vision tasks, they were achieved with using convolutional neural networks. So basically, it has in itself underlying two underlying ideas. One is the sparse connectivity. That is, in layers, neurons are not all the neurons in a layer in the first layer connected to each neuron in a second layer, but rather they have these sparse connections. And another idea is that the weights for the next layer, they are shared between units. So basically, you have that the vector of weights that are shared between different units in a network. And basically, how it works, it goes through the patches of images or data, two-dimensional data, for example, and basically it applies some linear filter to the patches of data, which is basically a convolution in signal processing, and goes through the batches of data, adding a bias term, and then those batches that are collected in a higher level layer in a feature map. And you can see that the whole architecture of the network would look like this. So this is a famous network from 1998 developed by Jan LeCun. It's called LeNet, and it has, so basically demonstrates how the convolutional neural network works. It takes those batches from the input layer and construct the feature maps using linear convolution filters. And after that it does downsampling in a feature maps, and it repeats for the few times until at the last level it reaches a fully connected layer of multi-layer perceptron, the classical neural network that you use for classification. So basically, that's the feature maps that are those levels when the hierarchical representations of features are built. And after some layers, after some iterations of those hierarchy building up, it's basically classified in the last layer. Real modern convolutional neural networks can get even more complicated, and this is the structure of deep learning method from the paper I already mentioned from 2012 that did a breakthrough in computer vision. And as you can see, it's much more complicated than the conceptual example that I showed you before. And I should mention that it's actually computationally pretty expensive to train models that are big and complex like that. But modern advances in hardware and algorithms allow it to do in days instead of weeks before. So when this group of researchers were developing this network, they spent weeks on training this network on few GPUs. But now GPU farming and CUDA programming allows it to do much faster. And another very important deep learning architecture, model architecture, is deep belief network. And to introduce that, I first start with just to remind what the energy-based models are. And basically, what the energy-based models are, that's the models that learn energy function that should take low values on a data manifold, on an input data, and higher values everywhere else. So basically, I think this is the good example of sort of getting an intuition what's the input manifold and everywhere else. So these dots are input data in two-dimensional space, and what you want to do to feed the energy function to them is to sort of make their values lower, the coefficients for them lower, and make the values for everywhere else higher. So that's the idea of the model that are based on the energy function.
Now notice this Facebook AI research and Center for Data Science. This is a big deal at NYU. Be aware of this, right? I mean, that's huge.
Yeah.
You know, and you know, some of these centers, and this is a good example, really making us at higher ed rethink the whole data science movement, because there's so much money in such a tight partnership that's going into these centers. It's not clear what, you know, a normal university with their paltry 50 million can do. So you know, it's really important. We've been talking to those guys a little bit. I'm sure you know a lot more than I do about this.
Yeah,
But it's important to see where this work is being done, and what groups are involved in helping to fund and direct this work.
yeah. So
This Facebook thing is an example.
yeah, Jan LeCun, he was one of the pioneers of the deep learning in general, and he was the professor of computer science at New York University. And after the important work that he contributed to the field, they made him the chair of the Center for Data Science, and he also was hired by Facebook Artificial Intelligence Research, which is pretty important because on using all these advances of deep learning, even such companies as Facebook, who are basically were doing social network in the beginning, they start to invest into artificial intelligence research, and that's the step ahead, right? And I think that's very important to keep track of the works that they do and the papers that they publish, because a lot of papers these days that are published not by universities but by Google or Microsoft or Facebook.
Yeah, it's a big trend. I mean, so the big trends in computer science was, before 2000, 9/11, right? There, the big thing was the dot bomb. So everything was building up, and then there was a big financial collapse because of the dot-com burst, and then computer science started taking it. And then it started rising up again, and it was quite popular. And then 9/11 hit, and then actually computer science became more popular, but most of it was classified. So a lot of it moved away from the academic sector. Or if it wasn't the academic sector, it was classified. And then these things, the new wave came up, Facebook, more Google, et cetera, and then it's amazing, but if you look at the undergraduates, say at University of Michigan, for example, I think 60% of the undergraduates in engineering college are declaring computer science as their major. I mean, they all want to, go and, have a $240, $3 billion, IPO, after 2 years with a bunch of their buddies and a couple dogs, and that kind of thing. And it's real. We're dealing with this right now. And, the other thing I think we're dealing with, so there's been kind of a cyclic. What I'm trying to say is there's a cyclic thing going on in computer science. And we should be really aware of that,
Yeah.
Talking about the impact of all these things on society.
Well, this is a great, in fact, there's an article that
separate this out to say the data.
Impact on society. Very good. I mean, it's huge. There's, for example, in January 30th of this year, which was last month, there was a whole journal of science devoted to what this is doing to privacy. So great, they can, the Holy Grail has been reached, and we have facial recognition. We can, frankly, pull faces right off of anywhere we want, airports, various security, Facebook, whatever. I mean, it's a done deal. So what's happening with privacy? So I was reading last night. There's a great article. I'll send you the PDF after lunch. Just a little thing by my friend Danny Goroff, who's now at Sloan as a VP over there. Just looking at various levels of identifiability of data that's supposedly de-identified. Okay, so in 2013, the state of New York published a de-identified, anonymized list of all the taxi rides in the city of New York City. Every taxi ride. Well, there were some little weaknesses in there. And, the thing is, you have your data over here, which is really protected, but then you bring in other data. And, the bottom line is, they were able to figure out every taxi cab driver's income. They were able to figure out the average fares. They were able to figure out what tips were given by probably which celebrities that actually, were in the cabs. I mean, whatever. So the societal impact on all of this, whether it's, hackers getting into your credit card or your health record, the idea of privacy is just literally out the window with this stuff. Because it is real, actually. And the question is, what are we going to do about it as a society? I think that's what you were asking. And we, kind of the, passengers along the ride of this, train, we have our issues with the health records and the identifiability of, genomic sequences that are merged with other things, which are the ultimate identifier, much better than fingerprints. These are the tools and the methods that are getting us to this point in society where privacy doesn't exist, that our critical systems are vulnerable due to attacks from the outside, and so on and so forth. We have to do something about it. If we don't, who will?
Okay.
I'll send you the little article. It's worth reading. You can take a look, and I'll try to figure out, Marcy, maybe you can help me with this, try to figure out how we can get more of the articles from that important science magazine made available to the group. Okay?
Sounds good.
Go ahead.
Okay, so I'm just going to finish about energy functions, just to remind you where we stopped. That's you're trying to push the data down and everything else up. And one of the models that is probably a lot of people familiar with is maximum likelihood estimator. So basically, it does the same. It makes the data points bigger and everything else smaller. And when you do actually a minimization of negative log of maximum likelihood, you basically are doing the same, but it's just mirrored in an opposite way. And then for that, for optimizing this problem is usually used gradient-based method, something like gradient descent or something like that. And this idea lies in a base of restricted Boltzmann machines, which are basically artificial neural networks that can learn probability distributions over the set of input data, and they are actually represented by themselves as just a particular form of Markov random fields. And they look like this. They have one input layer and one hidden layer, and they called restricted Boltzmann machine because there is restriction that inputs in a hidden layer, they are not interconnected between themselves, but only to the input level. And for them, energy function would look like this, depending on the parameters of this model. And then you can calculate the conditional probabilities of getting the values for hidden layer based given the input and opposite, given the getting the outputs given the hidden layer. And deep belief networks is basically that's the network which consists of stacked restrict Boltzmann machines when you have multiple layers of Boltzmann machines, and then the calculations of the conditional probability looks like this. It's basically constructed from these probabilities layer-wise.
All right, go back to that energy function for a sec. I mean, I'm okay fast, but not that fast. Okay, okay, so now you have a two-layer thing. So explain me exactly what the Boltzmann machine is again.
So this...
I mean, you can refer to, statistical physics if you want. I mean, Boltzmann did what? What's the key critical idea? I mean, I think it's related to this other thing, your maximum likelihood estimator that you're talking about.
Yeah, I'm pretty sure it came from the idea of it came from the statistical physics.
Yeah, of course it did.
Yeah.
So what is the idea? I'm just trying to get the idea.
To minimize the energy function here.
Okay, so if you wanted to, so that sounds more like GIP. So, but whatever. So you want to so when you minimize the energy function, what does that mean? So you're looking at the free energy, so you're looking for some kind of local minimum and some kind of energy landscape.
Yeah, that's the energy landscape, and you want to see the inputs in a local minimum. So when you slice it like this and in between, you can actually separate the data that you have from everything else. So basically, you're looking the minimum here for the data points that you have.
I see. So if you have this multi-layer thing, that there's some kind of and then there's the assumption, I guess, that you have a relatively continuous function. There's some kind of landscape in every layer, and then you apply this Boltzmann machine in every layer.
Yeah, it's basically constructed from Boltzmann machines, and
layer
that's
by layer.
Layer by layer. So, you know, so you have this layer thing, and on every layer there's some kind of energy landscape, and then you apply a Boltzmann machine to that layer, which gives you a way to actually find the various local minimum in this, in the, kind of a contour topology of the energy landscape, layer by layer.
yes,
So that's what actually you get out of this.
that's what it is. And then
All right. So now you got that. Then what?
when you use connected layers, use the data from the previous layers. So you have these feature representations that I mentioned before. They build up one after another one as it goes from the first layer and further. And so that because of that, they can be trained in unsupervised way. So basically, they learn the probability, the conditional probability distribution over those over those nodes in a network, and then they basically work as a feature detectors. That's the hierarchy of features that I was talking before.
So is the inputs and the outputs kind of like one layer to the next?
Through the layers. So basically, you have
They still do back propagation. Right?
yeah.
Yeah, and I guess that's what those dotted lines are coming up.
Yes.
That's
So
the back
basically-
propagation.
So these are layer by layer, just the initial
Yeah.
weights of the back propagation, update.
So that's what I mentioned before. You can first you train the model, and then you do the back propagation to update weights in
And then you
in
just
all
do
layer
that until you
until you
converge to something that looks like this,
yes
the object
exactly
itself.
exactly.
All right. Well, how many? That I can understand. So
Okay, good.
I guess it depends on how much sampling you have. So I mean, this is when you get into Nyquist. I mean, you have to have a certain degree of complexity in your space to pull this off and have enough. Otherwise, wouldn't it be too sparse? When I mean, I'm looking at smarter people than me, but I'm just, you know what I'm saying? I mean, you have to have a certain amount of data
Yeah.
in the system to begin with to slice it up that way and have any prayer to
So
find these
basically-
various energy landscapes. Isn't that right?
Basically, all the data first goes to the first layer, and after first layer is trained, it pops up to the second layer. So it's trained layer wise, basically.
Okay.
And then you have a back propagation that updates the weights in each layer.
Okay, so this thing here, then you have a probability distribution function that's keyed up on these layers, and then you convolve all these. And then what does that other thing actually say? What is the right-hand side of the equation? What is that telling us?
So basically, these probabilities that are they are learned they learned feature representations from the input data. So basically, they I can actually show. I have a picture, something like that.
Go ahead.
So when this the whole machine works, the deep belief network works.
All right.
In here in the input layer, that was just your data first,
Okay.
something that you put in there as an input.
Okay.
It after going through the iterations through the machine, those features that are edges, dots, intensities, they become something more complex. They build up the hierarchical representation, because from here you have only pixels. Here you already build up edges, and as it goes through the layers, from edges to some features of the face, and to the faces somewhere at upper level. Hierarchically, after it goes through all these layers, it represents features of inputs as complex representations that are built up hierarchically. If it's clear.
Starting at the top row from left to right, each sample is generated after 100 steps of block Gibbs sample.
So basically, starting from here and here, it was those representations were taken out of the deep belief network and represented as image, and you can see how feature faces are not very clear here in the beginning, and how much more like face they look in the end. So basically, as the training goes, they improve through the back propagation, and through the retraining, they improve the representation of those faces more accurate.
Okay, so this is a training thing, so not you're training so that you can actually do feature recognition over.
It is unsupervised learning. Yes, you just provide the inputs, and as it goes through layers, it can learn these complex representations, complex features.
So what's kind of the compute? What's the compute overhead for something like this? I mean, biggest system do you need to do this? I guess it all depends on how many faces and how many inputs.
Yeah, it depends.
What kind of system do you set up to do this?
Depends
how
on
much data would you need to make it real? I mean, yeah, go ahead.
So I have a really naive question. Maybe someone can educate me here. So they say they are doing better than human, the ImageNet data, but the ImageNet was originally annotated by human.
Yeah, exactly.
So they are saying their new students are less smart than their old students.
That's one way to look at it, yeah. That's a good way to look at it. Yeah.
That's a very good question.
Yeah, I don't know, first of all. And I think that probably when it was labeled, that was some kind of verification or agreement. Maybe they did, you know, there was not one person who was labeling the data
Right,
set.
but only 2 students participated in labeling that data, as far as I know.
Okay. So yeah, I'm not sure. Yeah, maybe that's not exactly correct to say that's the human recognition level is set at that benchmark that was 5%. Maybe that's not exactly correct because there is mislabeling in a data set, and maybe the model actually recognizes better than it was labeled in the beginning. But
maybe it's just the old 2 students are very smart.
Yeah, right.
they were very patient. They Googled every picture. Yeah, not sure though. And so yeah, that's the result of the feature representation that you get when you're training the deep belief network. And in the end, when you have these features represented hierarchically, you also can do a supervised classification on top of those representations that you learn from data. And just to finish, I'm including a lot of links to different results. And one of the critique points that usually address to deep learning is there is not enough theoretical background, not enough explanations how it works inside, how those probabilities are built, and how the what actually is going on in between hidden layers. And I should say that recently, in last 5-7 years, there have been a lot of theoretical investigation in that area. And here I just give few examples of actually books written on a deep learning by leaders of the area, such as Yoshua Bengju and it's hard to pronounce the last name, Schmidbacher. And there is a really nice class for everybody who is interested in deep learning. I would refer to that one. It's the class that they teach in Stanford this semester, and it's about convolutional neural networks for visual recognition, basically for computer vision. It's an very interesting class, and they publish everything online. They have a code on GitHub and slides on their website. Also, there are free tutorials for that can sort of either for implementing those models, or some of them also investigate some theoretical aspects of deep learning. For example, this is really nice tutorial that I liked a lot. Talks about statistical view of deep learning and represents deep learning as actually recursive generalized linear models. So I would suggest to look at that too. Another nice moment about deep learning progress in few recent years is that a lot of software that Dr. Rede mentioned was proprietary at some point, was used for companies' needs. A lot of that software is getting open source now. So all these tools that I show in my slides were developed at some point in different companies. Startup ML, Torch is underdeveloped with Facebook, but all these tools that getting open source. So you can actually go there and not just use them as a black box, but get inside and see what's actually going on in the source code. And I'm not sure if I have.
Before you go to the demo, I think there's a question that was asked very, very early on. When you have these deep learning, well, you got two kind of goals here. One is classify. Tell me what this thing is. The other is tell me why. And can you get to the whys of things out of these?
Yeah, that's kind of what I was asking.
In other words, can you extract useful information for models for human understanding of what's going on?
You mean going on in data?
Yeah.
So basically, yeah. For example, those feature hierarchies, right? So they.
A lot of times, those are weird combinations of things.
Right. So here I can state it, and I think this is a property of the Boltzmann machine, but don't shoot me if I'm totally wrong. It's something called a state function in thermodynamics, and it simply means that you know the beginning and you know the end, but you don't know the path. And I think that these work like a state function. I don't think you know I think the thing that's been frustrating is that this might be totally wrong, but I think it might not be, and I think the frustration is you don't know what's happening along the path. You only know the beginning and the end.
But a lot of.
It's another way to say what you just said.
I think
so. This is a very useful. So it's called a transformation. So if this is a Boltzmann machine, you go back to the thermodynamics and the statistical mechanics, and you think, what is a Boltzmann machine? And then you dust off your thermo and your statistical mechanics course, And ultimately, what I'm saying is it's an analogy that's actually fairly strict. So and you mentioned Gibbs samplers and so on. Same thing. I mean, they are only state functions. They don't give you the path. And so and what folks want or something. That's why I'm asking about the black box. I mean, so I was kind of excited to learn about these landscapes, but then I was trying to understand, do the landscapes, the various levels, do they map anything that you can, do they represent anything that your mind can comprehend?
But that's
I think the answer is no.
That's basically, if you look at simple logistic regression, when you estimate parameters with maximum likelihood, it's doing the same task. And I mean, from the same point of view, you can say that you don't know what's actually going on in logistic regression.
But it might be, and I'm so sorry, for all of us to think about, it might not be possible with big data and all this kind of stuff to actually know what's going on. I mean, we might have to be, and the fact that you get outputs that are working so well, then you have to say, does it really matter? I mean, then you have to rethink about what we're doing here. If the damn thing works with such good fidelity, and then you can show how it works, prove it to yourself. But you better go back to some of what Fangwan is talking about in terms of, the original training, where the origin of some of the stuff with regard to training and all this. Where is this all coming from?
Okay.
So it's a good discussion. I mean, I'm just trying to get a discussion going. I think it's worth talking about. And I know in the lab meeting, because here, surprise, surprise. So what are you showing here?
So this is a simple demo just of
this is kind of like a
character
reader,
recognition.
A character recognition.
So
piece.
yeah, that's the representations that model learns level by level. That's the input that you give. And it's not just a video demo or something. It's the real network working in browser because it's written in JavaScript. So it's possible to train not too big networks written in JavaScript and run them right in the browser. And here is the classification result on a test set. And you can see that for handwritten recognition, even not very big deep neural network can recognize fairly well written digits.
How fast can it do that?
Oh, basically from the beginning.
Just
It's really quick.
Yeah, we had a contract which actually led to there's a company in town called Novo Dynamics. You know, I think some of you guys have heard of it. It's down off of First Street.
So first,
they did that. So that was I had a group way back when in the day at IRM that you know.
So now it's mostly red, but they're gonna.
I mean, we did this. We had a contract with the post office department years ago, and my group read envelopes in a secret room way back down in IRM. We figured out how to read the addresses off of envelopes. And then somebody else got the bright idea, if we could read envelopes, maybe we could read things that were written in Arabic, right? Then we started to read Arabic pretty well, and then that turned into an industry. And then they spun off. They ran away. They got tired of me. They created a company which became Novo Dynamics, and they were working on using some of these methods in the early days. You know, precursor. It was pretty primitive, but you know, this is like 25 years ago. You know, Alex, you might remember some of this, right? Very well. Okay.
So it's.
But now take a look. I mean, there's no arguing with success. I mean, it was really, you know, it was really pretty stunning and spectacular at the time. Why? Because those are just handwritten. I mean, they're pretty ugly. It's hard to deal with that. But it looks like it deals with it very well. Look at those twos.
That's a standard data set.
Yeah, you know.
And I'm saying, instead of conclusion, the idea would be if it is working for pedestrian detection or 3D natural image analysis, why it cannot work for medical image analysis, right? Obviously there are different challenges that are present in biomedical image analysis, but I think the potential of deep learning models, it's not completely discovered yet in this area, in this field.
Well, I think it gets back to what Jean-Paul was saying. You know, look, who said that humans were that good? See, this is, I think, part of the thing with the big data and all this. You know, there's no way that our mind can comprehend. So we like linear thinking, right? So we use the Fourier transform. Works pretty well for us. I mean, you can, you know, from beginning to end. But, you know, this is nonlinear stuff. Our mind does terrible with it. The questions become so complex. So if it's a radiology image or some histology image, so we had something down, and I haven't told you about it, you know, when I was in Hopkins. So we had some kind of 2D classifier on the 2D images, you know, of these Gleason graded specimens coming from the pathology lab. But we had the data, you know, does the patient, you know, get prostate cancer quickly? It's all retrospective or not, you know, that's the question. Well, you know, with 89% fidelity, Bob Beltry, name you know, was able to, in 2D, you know, see things in the Gleason graded histology slides that the pathologists simply couldn't see. So this model, you know, and, you know, with 89% fidelity, found the guys that progress rapidly to prostate cancer versus those that don't. I mean, that's the holy grail. It's in the histology. It was always there. Our machine learning can see it. The pathologists can't. The point is that there's a lot of things in the data that the human will never see. And that our mathematics and our models, you know, are, you know, so primitive. Now you're bringing, you have more data, more complexity. The point is that there will be, the whole promise is there's lots of stuff in the data that we can't see, we don't know how. We can just see kind of the outputs that we recognize in a glyph that we know, like this. I'm sure it's true. And so the answer is absolutely. There's all kinds of stuff in medical imaging that humans and pathologists and radiologists cannot see. That machine learning or... Now, go back to your title and let's see if it hangs. What's your title?
Oh.
Yeah, go back to the first slide.
Okay.
I just want to see whether we believe you or not.
I answered it already.
I know. I just the end of machine learning. Well, I don't know. You know.
Oh,
I signal processing. Well, you know. Why don't you explain yourself on this one a little bit? I mean, I can kind of wrap my head against Yeah, right. Generally,
I have-
Evolution of machine learning and signal
I have a very simple explanation. I actually borrowed this title.
all right, he stole it
that
from
was
the
a panel.
guy.
Last year it was panel discussion with machine learning experts in a world class machine learning experts, and they have a panel discussion titled like this. So I sort of borrowed it from there to get more attention, and worked.
But you know, I think that I think it's the evolution, Alex.
Oh.
You know?
I just have a separate question. But
Yeah, well, I think it's the evolution of machine learning. That part.
Definitely. One.
Signal processing is another subject. I mean, and there is a form of signal processing related to imaging, I guess.
And there is a theoretical investigations relating actually deep learning, explaining those mechanisms from the signal processing point of view. That's.
So I think a better title for this might be the end of machine learning question. Signal processing is a completely different field, and we didn't scratch the surface of it in this talk, so it's a little bit too broad.
Alex?
That's my opinion.
yeah, I was just curious. You had a slide up there where you list some open source packages. Have you tried any of them? And have you tried any of them on?
Have you tried any of them on the things that we care about in the lab that we're like tripping over, like I'm making an idiot of ourselves?
It's for me personally, the hardest part would be is to take the data that we have and use it in that software, because like image representations that we have, that very specific, that software potentially can be used on that, but you have to have those representations, how you go through the layers of the stack, and I'm not exactly sure how even start, because these packages, they can work with like numeric data, for example. Some of them has some common image adapters, but if you want to use any of this software on a 3D imaging from the confocal microscope, then you have to have this data reformatting and representation.
So we should look at that in the lab meeting, and and have it. Let's actually look at these tomorrow at the lab meeting. I think that would be good. One other comment about facial recognition. I mean, I don't get the 50 muscles. I mean, I can see the tip of the nose, the corners of the lips, something about your ears. It's called landmarks. That's, I think, driving the facial recognition. The muscles you can hardly discern. So think about it.
No, but it changes relationships between different parts.
Yep.
So if you get a person with somebody shouting, they look very different from someone.
They do.
Well, no, by the way, so this is.
So it's not really modeling the muscles, but it's got to account for the fact that all these things can change.
Well, I think that's a very perceptive. I agree with you on that, 100%. And then that's really something that's very cool about all of this, and it's kind of capturing more dynamic information as part of the because you're dealing with snapshots. But at the end of the day, and this is applying to movie. They're running this on movies and everything as well, like YouTube videos. And stuff.
Yeah, if person is smiling, if it's crying, shouting, right during the video, not just taking snapshots.
Yeah. Right, and I can imagine if you had surveillance cameras, it's not just getting snapshots, but it's watching somebody go through the line. Yeah. Like when they ask you the question, they say, "Thank you, Mr. Wright," when you're going through security, and like, I imagine if you're Mr. Right, you have a certain facial expression. If you're Mr. Wrong, you have a different facial expression, you know what I mean? And they're probably capturing that.
All right.
Thank you, Alex.
Yeah,
That's great.
Let's go.